Good afternoon. Last time we talked about cryptography, and I want to finish that today, hopefully. So the last thing we tried to talk about was, uh, we started with symmetric encryption, and then we moved to asymmetric encryption, and we kind of like the last thing we tried to talk about was RSA trapdoor function, and it kind of explained what is an RSA trapdoor function. And we said that essentially most of the time asymmetric encryption is used as a hybrid encryption mechanism, not really kind of directly being used. That's why we introduced the notion of hybrid encryption, where we kind of like the key is encrypted using uh, asymmetric method, and then once the key is kind of communicated, then you just continue with the symmetric. The reason that symmetric is much better than asymmetric is that symmetric is significantly faster than asymmetric encryption, because asymmetric requires very large size data. So usually like key for RSA needs to be thousands of bits, versus usually the key for AES is kind of in the order of 256, 512. And then the operations in RSA is usually exponential operations, modular operations, versus if you remember about AES, most of the operations kind of linear operations, right? Like you mix columns, you move things around, basically. It's kind of trying to create permutation. So much, much faster than, like, for example, computing an exponential and so on and so forth, or a modular. This is just generally something to remember. Uh, I specifically talked about this the key encapsulation mechanism, and said that basically in one go we can send a symmetric key as well as sending a message. And then after doing this, like basically the fourth step was just a regular communication using symmetric, right? And if you remember, essentially we create this random number x. We use x in order to compute y. We hash x to create the key, and then we use symmetric key to send the C, and then we send C and Y as the input to the system. Decryption was kind of like reverse process of that. We take Y and secret key, we compute X, we hash X, get K, we use K to decrypt and get the message M, right? And that final point here, I have the message and I have the key. And from now on, I can just kind of move forward with the K and symmetric key all the way forward. That's kind of like the most important thing about chem. And then, as I said, embedded in this chem is these two important functions. The F function, the forward kind of trapdoor function, and then the backward one, which we usually either use I or F inverse. And these are the kind of like where the RSA is specifically, for example, in this example, comes into the play. But this F and F inverse can kind of substitute it to any other trapdoor function. So as I said, for example, elliptic curves and other examples and so on and so forth. Okay. Yeah. And then I kind of like at the very last part of the previous lecture, I tried to kind of give you an example of how RSA trapdoor function works. Hopefully you kind of took some time and reviewed it. Just very basic kind of review of this again. The idea of RSA trapdoor function is the first thing is we pick two prime numbers. These are the P and Q. Usually, as I said, in around 1,000 of bits, and they have to be prime, otherwise the rest of the things won't work. So the generator function, if you remember, that was kind of generating the P and K, the private key and symmetric key, secret key, the public key and secret key was in order to generate kind of two numbers. Here, these two numbers has to be prime, P and Q, has to be very large. Then we kind of do some set of kind of definitions. First of all, we define n as the product of P and Q. Then we define phi of n as kind of like the co-prime factors of n. And this is just basic mathematics that, if the number is a product of prime numbers, co-prime factors is basically just the product of prime numbers minus one. So p minus one, q minus one. Again, this is the Euler function, very famous kind of very, very useful and popular function. But anyway, if you just don't remember anything, just know as a fact that if p is a prime number, phi of p is equal to p minus one. And these are just co-prime numbers. The numbers smaller than p, that if you divide it by p, the remainder would be one. It's not divisible. Sorry, it's not divisible by p, right? So yeah, it's just kind of like, here I gave you a definition that it counts how many numbers less than equal n that have no common factors with n, right? In other words, co-primes. And then based on this definition, phi of n is p minus one times q minus one. The reason that this is important is that when we are actually decrypting, we are going to use this fact that I'm going to show you here. Okay. So then how do we actually do the encryption and decryption? So once we kind of define this n and phi of n, then we pick these two important variables d and e, which in some sense are private key and our public key and secret key essentially is based on these d and e. So how do we pick d and e? D and e should be chosen such that their modulo by phi n is equal to 1. In other words, ed times some factor should be equal to phi n some factor plus 1, right? So if I divide e times d by phi of n, the remainder should be equal to 1. That's kind of like the definition, okay? And so how do we pick these two? We typically do this by making one of them constant, and the other one we search through in order to find a number that satisfies this equation. Okay. In most cases, we kind of, since e is part of the public key, we usually like make e constant, like 3 or 21. This are different numbers, and then the d part is just we search through the numbers, we iterate through from 1 all the way to whatever number, such that we find a d that satisfies this equation. Okay. So now we have e and d. These are two numbers. Then we're gonna build our secret key and our public key this way. We're going to call public key n and e, and the secret key is n and d. In other words, we keep d and we share e, okay? And then the big thing here is phi of n, computing phi of n is not easy, okay? If computing phi of n was easy, then people could have easily find d, right? Yeah. People could have easily find d, right? If I have phi of n and if I know e, then I could easily find d, right? But so the whole point of RSA is that if I know n, finding phi of n is not easy. Why? Because I know that n is equal to p times q. So in other words, if I know n, finding p and q is not easy. In other words, breaking down the number into its prime factors is a hard problem. This is actually a known hard problem. For smaller number, this is not a hard problem. For example, if I tell you that, I don't know, like 33, right? What are the prime factors of 33? You could easily say, 3 and 11. You basically run like a 2 for loops and then find them very easily. But if the numbers is large enough, then this will take, a lot of time. And since there is no known algorithm for doing this efficiently, you just have to brute force through, through the numbers. And if this number is big enough, then there's no fast and quick answer for this. Okay, that's really why RSA function is RSA trapdoor function is a secure function. So there is formal proof for this that I'm not really talking about here. Probably some of you might seen it in some algorithm class that you have taken, but if you didn't, you can just search, prime factors of a number or factorization problem, and you will see lots of articles and things about this. Okay, so based on this, what is the f and f inverse? F is essentially x to the power of e modulo n. That's all you need to do. And f inverse is the opposite of that, is y to the power of d modulo n. And then if you can see that, everybody knows E because E is part of the public key, so everybody can, compute F. In other words, everybody can encrypt, but nobody can decrypt because nobody knows D. Only the receiver knows D. As a result, only the receiver can compute F inverse, right? And then in order to understand why y to the D modulo n actually is equal to X, you have to kind of like break this down this way. So y itself is x to the power of e. In other words, y to the power of d modulo n is equal to x to the power of e times d modulo n. And then if you remember, I told you that e times d modulo phi n is equal to 1. In other words, e times d is k phi n plus 1, right? So it's some coefficient of phi n plus 1. And if I basically opens this up, this means that this is e to the k phi n times x, right? So I'm just saying that x to the power of k phi n plus 1 is, in other words, x to the k phi n times x. And then there is this very another known algorithm that says that if the greater common divisor of a and n is equal to 1, then a to the power of phi n is equal to 1 modulo n. This is another theorem very well-known theorem in mathematics called Euler theorem. So in other words, x to the phi of n, this should have been phi of n, is equal to 1 modulo n. So in other words, x to the phi of n times x is 1 times x. In other words, it's x. Okay, so that's how we actually, from y to the power of d mod n, we get to x to mod n. That's exactly what you want, right? And again, I think the easiest way to kind of understand this is trying to derive this math for yourself, and you will see how from y to the power of d we get to the x. Okay. So yeah, this is kind of it for this. So few discussion points. I already discussed this. So key distribution from symmetric versus asymmetric. The biggest advantage of asymmetric is that you don't need to do any key distribution other than kind of publicly announcing your public key to everybody else. So all you need to do is knowing what is the public key of the receiver that you want to send the information to. That's really all it takes. As a result, there is no secret communication required between the sender and receiver. Versus in a symmetric key scenario, you had to first start with some form of key exchange algorithm, which was not trivial in many cases. The second thing is the speed, and as I already said, symmetric key is significantly faster than asymmetric. That's why we really want to do symmetric in most cases. That's why in most of the devices that we use, we may not even be able to support asymmetric. For example, in embedded systems, actually, typically we don't use like RSA. It's always like symmetric encryption. And in terms of security, both of them are based on hard problems. Both of them achieve semantic security. One difference between them was symmetric key has to be CPA secure, which means that it's chosen plain text attack secure, because the adversary cannot decrypt arbitrary messages, and then they cannot encrypt arbitrary messages either. But for asymmetric, it has to be CCA secure, which means that since the adversary can encrypt arbitrary messages, they have access to pairs of known plaintext and known ciphertext. So our system should be secure against that. So it's a slight difference between the security of these two. And then again, hardness of RSA trapdoor function is based on this integer factoring problem that more formally, the integer factorization problem says that if you're given a composite number like n that is a product of at least 2 prime factors, it's hard to find x and y such that x times y is equal to n. Okay, it's not efficient there is no known efficient algorithm that can find x and y in some bounded time. Okay. And then the question about this is factorization really hard? And that's where actually quantum computing comes to the play. Probably most of you have heard about post-quantum cryptography and kind of old cryptography makes the systems no longer secure. The reason for this is this factorization problem. In fact, there is an efficient algorithm in quantum computers that can actually find X and Y in very, very short time. And as a result, this assumption that integer factorization problem is a hard problem is no longer true for quantum computers. Okay, so one of the main things about quantum computers, especially in terms of security, is what we think that it was hard, it no longer is, if we actually manage to build good quantum computers. To achieve this, actually, we need really large quantum computers. So we need quantum computers that has more than 1,000 qubits. We don't have it yet. What we have is in order of 100. But there are kind of signs and progress toward getting very soon to that kind of 1,000 qubit system. And once we have that, then we can use this known algorithm called Shor's algorithm, that based on Shor's algorithm, then you can use a quantum computer to break and find the factor elements of prime elements of a composite number. That's really why this is important. If you're interested in knowing more about this is an interesting video, a little bit long, but it's very interesting video about the relationship between quantum computers and cryptography. Another thing that I wanted to say is and the interesting thing that people are worried about now is that even though we don't have quantum computers that can break the kind of RSA algorithms right now, what people think is that an adversary can record data, right? And once, for example, let's say 5 years from now, they can break the system, they can now decrypt the messages that we are kind of transferring right now and use some knowledge. Or for example, I mean, the knowledge would be 5 years old, but still for some very, very sensitive matters, this is still useful knowledge, right? So this is another thing that even though that quantum computers are not like a big quantum computers are not yet possible, but still our quantum algorithm, our cryptography algorithms is not secure anymore, right? So that's why actually many of the systems right now even using post-quantum cryptography. Yeah, question.
I was just going to ask, is there any way to prevent that? So in the future.
So the question is how to prevent this. To prevent this, we need to move on from not quantum safe crypto algorithms to quantum safe crypto algorithms. So this is what we call post-quantum cryptography. That we find other trapdoor functions that are robust against quantum algorithms. And there are, for example, there's what we call lattice-based cryptography, which the hardness problem is based on lattices and not based on, for example, RSA trapdoor function. And people have shown that these are actually resistance against quantum computers. So we have to move toward that. So there are actually probably you've heard about Kyber algorithm. There are there's actually similar to what we had in early 2000 for AES. It's now going on for post-quantum. So NIST is actually trying to find the standard post-quantum algorithm that everybody could use. And they're actually, I think now it's 2-3 finalists or something. So very soon they're going to be one standard algorithm for post-quantum. Yeah, that's exactly what I said. Post-quantum cryptography is what we are moving toward. And then, yeah, if you're interested, definitely you can search, for example, how the lattice based. But I mean, that's the kind of the basics or the fundamentals are very, very similar. It's just that the fundamental mathematics is slightly different. Otherwise, it's pretty much the same. All right. Any questions about symmetric or asymmetric encryption? Yeah.
Symmetric and faster than asymmetric.
Why symmetric is faster than asymmetric? The question is why symmetric is faster, and it's really because the nature of operations. So, for example, if you remember in RSA, f has to be x to the power of VE, right? So this is just this is an exponential operation. You need to multiply two numbers together. But if you remember AES, most of AES was row shift, mixed column, just kind of moving things around. Another thing is that RSA needs to be very, very large. So we are talking about like 1024 bits and so on, versus AES, we're talking about usually about like 256 bits and so on. So just the number of bits like 4 times fast, like 4 times smaller. All right. So if you remember, I told you that cryptography is about different primitives, and we started with encryption, but encryption is not the only primitive that is very important in cryptography. There's also other primitives that's very, very useful and very, very popular and used very, very widely. And we're going to use it in this course as well. The first one is what we call message integrities or MACs. So the idea of MACs is this: that if I receive a message, I don't care about the confidentiality part of it. So I'm okay if the adversary can see it. But what I'm interested in is to make sure that this message that I've received is the exact same message that the sender has sent, right? Because, for example, what could happen is the adversary can, instead of sending this, kind of intervene and send me something else. So, for example, instead of sending yes, they can send no. And remember, encryption doesn't help, because essentially what the attacker can do is that if somehow they have kind of like the database of encrypted messages, what they can do is that they can just substitute this with something else, right? So send something or send something wrong to me, right? Sending an old message and so on and so forth. So the idea of message integrity is different than encryption, and encryption here doesn't really help me. Okay, so I need something else which we call message integrity primitive or MACs. And the idea of a MACs is very simple. The idea of MAC is that not only we send a message, we also send a tag with it, a metadata with it. And this tag is kind of like based on this generate or signing algorithm, that the signing algorithm G takes the M and computes the tag based on the M. Okay, and then on the receiver side, we have this verify algorithm, which takes the message, computes the tag, and check whether this tag is the same as this tag. So if these two match, it means that we got the same message. If they don't match, it means that we didn't get a message. We didn't get the correct message. Okay. So with this, what do you think it would be like a very simple attack to kind of break this? Any suggestion?
Like you somehow change only the tag.
But you want to change the message as well, right? So if I can't change the message and the tag together, so for example, I told you that let's say I want to send yes. So with this, I can send yes and the corresponding tag. Now the attacker, you want to say something?
Yes. Just going to answer your
Yeah,
question.
yeah, go ahead.
So each tag, the function is like deterministic, so each message will have a certain tag. And so if they send an old message, it will still pass the verification.
Yeah. So what I can do is that if I want to send yes, and then I need to send a tag with it, and if I want to send no, what I can do is that if I can compute the tag for no, I can send no with the new tag, right? So instead of sending yes and the tag, I take out the yes and I take out the tag and I send no with a new tag, which is corresponding to the tag of no, right? So I can substitute both tag and the message, and I can break the system, obviously. Yeah.
Is that G function known by the?
The G function is known by the attacker, but the G function is going to use a secret key similar to encryption, and that part is not known. So we're going to actually get to that. But yes, all the algorithms known. So you cannot focus on this fact that, oh, I make G secret. As a result, nobody can compute the tag, and then that would be hard. So in that case, what is a secured MAC? So what I described to you is a MAC, is a message of integrity. It's just a tag, but this is not obviously secure because the adversary can change the message and the tag together, and boom, the system gonna be back into the score one, right? So what do we need in order to achieve security in this system? Anyone wants to chime in and suggest? What's the like fundamental, property that we need to achieve to make sure that our system is actually secure? Yeah.
encrypting the tag also just like used for which making it probably.
So encrypting the tag might help, but again, if I have a database of tags and messages, can't I just also send, the way that I compute the tag may not be that much different, right? I mean, if I can replay it, I would replay it. But it's close. Any other suggestions? So what we need to do is what we call forgery attacks, right? We need to kind of protect our systems against forgery. And what we need to do is the attacker should not be able to compute a new valid tag for any messages in our system, okay? And then this is kind of like two-way, that for a given message, we should not be able to generate a tag. For a given tag, we should not be able to generate a valid message, okay? If you have this, we call that we are secure against forgery attacks, okay? So no valid pairs of M and T should be achieved. The second thing is that we should be able to protect against replay attacks, which means that if the adversary somehow has a database of previous tags and previous messages, those tags and messages shouldn't be replayed. So the message can, but the tag, each time we do the message, integrity, the new tag should be different than the previous one. And this is very similar to the way that we did it for encryption. And if you remember, we add some form of a nonce or a session key or initialization vector in order to fix that, okay? So similar tricks should be used here, that for each, even for the same message that we send twice, the tag computed with it is different each time, okay? So there's no replay tag. If it is, then our system won't be secure. So how do we actually compute tag and how do we actually use the MAC? We can actually, if you remember the pseudo-random functions that I described last time for a block cipher, we can actually use that in order to generate a tag. So how do we do that? Remember that we had a key and a message, and I told you that F is this function that maps this domain into another domain, right? And it's very, very hard for an adversary to detect and distinguish between this mapping and any other random mapping, right? So we can use that in order to compute the tag, right? So the output of that pseudo-random function becomes the tag for this particular message. And in order to add the nonces and all those tricks, we can use exactly the same format that I told you about AES. That remember that we don't really, do the message directly, but what we do is that we first encrypt the nonce and then XOR the encrypted version of the nonce with the message, right? So this was the trick that we use in CBC, for example, in AES, that we generate the nonce each time, which was kind of a counter mode. We just increase the counter. We encrypt it using, for example, this pseudo-random function. We get the kind of a random value, and then we XOR that random value with the message, and that would be our tag, okay? And of course, the tag should be long enough, similar to the way that we talked about AES. Otherwise, if it's short enough, then you can just brute force over, right? So if I can do this, then essentially whatever we talked about the security of block ciphers directly applies to the tag and MACs as well, okay? So we don't need to kind of reinvent the wheel in this case. Just whatever we do there, we just keep repeating here, okay? The second question becomes is that, okay, if I have multiple messages, how do I do a tag for those messages, okay? So similar problem that we had in block cipher was, like, if I have multiple blocks, the question was, how do I kind of encrypt them? And if you remember, I told you that essentially we're going to use this kind of, we need to kind of make them connected to each other somehow. And then if you remember, we started with like a nonce or initially a nonce and a counter. And then we call this together, we call this an IV. We send the IV here encrypted, then XOR it with the message, and then send it here. Here, we basically do the same thing, but this time we increment the counter by 1 and then do the same thing for the message. And we keep repeating this, right? So the counter and the nonce is kind of like the connecting factor between different messages. For MACs, we need to kind of also come up with some form of solution. One way of we do this is what we call nested MAC, NMAC, or cascaded MAC. The idea of cascaded MAC is this that let's say I have multiple blocks of message that I want to compute a tag for. I don't need to like send a tag for each one. What I can do is that treat them as just one giant message and then send one tag for the entire message. Much faster this way, right? So how do I do that? I start with essentially like I start with the key and then with the M, the first block of the message, and then send this to my PRF function. I'm gonna get a results. Instead of sending this results directly out, I'm gonna feed this into another PRF. This basically becomes the new key, and then this is a new message. And I keep repeating this until I get this T. The important part is I need to do another round of F, this time with a different key, to get the final tag. The reason for this is there are known attacks that's kind of like called extension attacks. If I keep doing this, then an easy attack to this system would be that the attacker just combine two messages together and create a new tag, right? If I just add another block to this, and then I just keep doing it with the same key, the results would be the same. So the attacker can easily extend this attack. We will see it in your first computer assignment. So as a result, what we need to do is that we need to do this twice with two different keys, such that the attacker cannot really extend and adding more blocks to the system. Because the next time the attacker wants to add a block, this part will be the same, but this part will be different because kind of the message that goes into this part is now different. Yeah.
Where does the nonce come into play here? Is that added with the first function and carried on?
So the question is where the nonce coming to play here? Yes, the way that we kind of like generate this K should be changing each time with the nonce. Any other questions? Yeah.
This like even for creating tag using the message and event.
Say it again.
So in this one tag is encryption of you are encrypting the message with event.
It's not encryption because if you remember, encryption was like multiple steps, but you are using a PRF to compute the tag, right? So you just kind of use some part of what it used to be an AES for this. So you're computing a function, a pseudo-random function.
That includes both the
Yes. If you remember, for example, that F in AES that got a key and a message, and it was like 10 round of like add round key, call and switch, that could be your PRF. All right. So as I said, the last round is required. And then the reason that we kind of like padding it is also is that if the tag is smaller than the size of the message, we can pad it. And let me see. And then there is also, so this one is kind of like serialized, right? So you kind of like compute the first one and then feed it to the next one and then feed it to the next one. There's another version of this called PMAC or parallel MAC that kind of like computes this in parallel and then combine them together. I didn't show it here, but if you're interested, definitely search PMAC and you will see how that work. But just remember that we kind of like, the main thing that you should remember is that we use two different keys. And then we kind of feed the message to another round in order to make sure that we have kind of connection between the message parts. Okay. So that's it with the Macs. So as I said, like CMAC and NMAC and PMAX are the most famous ones. I'm gonna actually come back to the Macs. It's called hash Macs. That's kind of the most used one. But for that, I need to first explain what is a hash function. Hash function is probably something that you have seen a lot in your life. Hash function by default is not a security concept. It's just, something that we use in many, many different cases. Generally, a hash function is this function that takes an input. We usually call it a key or the input, and then kind of map it into some smaller domain. The reason that you want to hash something is that you get an arbitrary size message, and you want to kind of map it into kind of a digest, a smaller size, what we call hashes, right? So instead of like storing this giant thing, you store this hashes. And the result, since the size of the key and the size of the hashes are mismatched, usually the size of the key is much, much larger, then there will be collisions, right? There will be the messages that map into the same hash, because we were talking about like a larger population that is mapped to smaller population. So of course there will be collisions, right? And the collisions is a known problem in hashes. And again, it's not necessarily a security problem, okay? So what is the secure hash function? So the secure hash function is essentially dealing with this collision problem. Okay, so secure hash function should be a function, a hash function that is resistance against collision. What is that? More formally, let's say we have a hash function h that maps the input domain m to an output domain t. Okay, and of course the size of the m is significantly larger than the size of the t. That's the whole point of a hash. So we call collision of h is a pair of messages m0 and m1 that's part of this message domain m, such that the hash of m0 is equal to hash of m1, while m0 is not equal to m1. If I can't find two messages m0 and m1, that is that their hashes are the same, we find a collision in this hash function, right? So a secure hash function is collision resistance if there is no efficient algorithm A that can find a collision in H. Or in other words, the probability of finding a collision is very, very low. It's negligible. Okay. So if we can have a function like that, then we call that this is a secure hash function. Okay. So not all the hash functions are secure, but if I can find a hash function that's looks very similar to a random function, to a random mapping, then it would be very hard for the adversary to kind of find two messages that produce the exact same result, because essentially all the mappings are random, or at least random looking. So the adversary has no idea other than brute forcing. And if the size of the message domain is large enough, then the adversary has no probability of finding this, right? In other words, if you remember, it's kind of like becomes 1 over m, and if the m is large enough, then the adversary cannot find a collision easily. Okay, so when we say a secure hash function, we usually refer to a collision resistant hash function, that the probability of finding the two collisions is very, very low. Yeah, there's also two other things that is important for us in collision resistance. It's kind of like derivation of collision resistance. And that's what we call a pre-image resistance and second pre-image resistance. So the definition of this is that if I have h of n, if I have a hash function of a message, I cannot find what is m. Okay. And the second pre-image is that if I have h of n, I cannot find another message that has, that hash of m prime is equal to hash of n. That's very different than collision resistance. It's kind of similar, but so this is a particular one. So for example, if I send you this hash, you cannot find another message that has the same hash. The collision resistance says for any two messages, it's not like this hash, just give me two messages that has the same hash. You cannot find that. And if you cannot find that, that's what we call a collision resistance. So second pre-image, slightly weaker notion of secure hashes. It says that if there is a known hash, you cannot find a message that produced this hash. You cannot find another message that has the same hash. Okay, so this is kind of like the idea of pre-image and second pre-image. Collision resistance is usually the strongest one. Says that there is no any two messages that you can find and tell me and say that, okay, these are the two messages. These are the hash for those two messages. Okay, questions? Okay. So difference between hash and max, they're kind of relevant, but they're not the same. First of all, hashes are keyless. In other words, anybody can compute a hash. There is no secret about computing a hashes. Adversary can compute a hash. You can compute a hash. Anybody can compute a hash. The security notion of hash is that I cannot find the message that corresponds to this hash. Okay, I cannot reverse it, in other words. But I can compute it. Okay, so it's kind of like similar to the notion of asymmetric encryption, and even the adversary can compute, but the adversary cannot reverse. The max it's different. The max use the key. In other words, the attacker cannot compute the MAC. Okay, if the adversary can compute the MAC, it means that the adversary has access to the key, which means that the system is already broken. Okay, so MACs are very similar in that notion to symmetric key encryption, versus hashes are very similar to what we call like an asymmetric encryption case. Okay, and then your use cases are slightly different. MACs are for integrity checks. Hashes is kind of like this workhorse for many different things. You have already, for example, see hashes are used in KEMs, the key encapsulation mechanisms, because we wanted to shorten the size of the key domain, or we wanted to make sure that the domain is uniform enough or random enough. That's why we use hashes. So hashes are usually not really directly used, but it's used in some form of a bigger protocol or bigger primitives. Okay, so that's the difference between hashes and max. And of course, hashes are much faster than max, because usually in order to compute max, you need hashes. So a very famous and very popular one is what we call a hash MAC, an HMAC. HMAC is a MAC, it's not a hash, it's a MAC, but it uses a hash in order to compute the MAC. How does it work? It works like this, that essentially, remember that kind of F function that I talked to you about, and say that, okay, let's have a PRF, and let's feed the input and the key, and then kind of cascade this through, and then you will get your MAC. So here the idea is that, okay, I have hash functions, and hash functions are good enough. So instead of having a PRF, let's use a hash function, which is significantly faster, and kind of like apply the same idea that we had before. So how do we do that? We essentially start exactly same thing that we had before. So we have kind of like two keys here. This is my K1, this is my K2, and then the rest, if you look at actually from this part, you will see that this is exactly the same way that we had an NMAC, right? So the NMAC was, if I go back, the NMAC was key here, message here, FFF, all the way to here, then another key here, and another F, and then tag. The HMAC, essentially what it does is that instead of this F, change this to H, and then do the exact same thing. There are like slight differences, but in general, that's the idea of an HMAC. Why an H is better than an F? Because hashes are very fast to be computed, versus F is kind of like this AES algorithm, for example, that's kind of like required lots of rounds and so on and so forth. So HMAC significantly faster than a regular MAC computation. Okay, so there are details such as how do we actually compute this, how do we add nonces and so on. So usually, as I said, the nonce part is embedded inside the key one. So we usually start with the initialization vector. We use the key and then computes the MAC, and then we compute this for the rest of the messages, and then we go all the way down, and then here we need to create another key, which we usually you do it with using another K with another padding. So we kind of like generate two different keys and then feed it into the system. Okay, there are like differences, like how do we do the padding. This is kind of like this, if your messages is smaller than the size of the input of the hash, you have to pad it and so on. So these are the kind of like the smaller things, but the big thing is this H function significantly faster than any sort of pseudo random function that we have. Okay, any questions about max and hash? Yeah.
Can you clarify the little h's there? Are each of those h's a separate hash function?
Yes.
As a result of one hash?
Each of these little edges are a hash function, but it's just the exact same hash function that you repeat over and over.
Oh.
Yeah. So for example, you've probably have heard of a SHA, secure hash algorithm, like SHA-256, SHA-250, 512. So these are usually this H functions here. The H should be a secure hash function. It cannot be any hash function. Okay?
Can you clarify again why H is faster than F?
The question is why H is faster than, because if you look, for example, into the SHA, you will see that it's like, again, the nature of operations is very simple. So it's a few operations, doesn't require that kind of 10 rounds of columns and mixing and all those things. Yeah, that's really what it does. Just simple operation, less operation, simpler operation. But again, just keep in mind, very, very important, not any H should be used here. Only secure hash functions that are collision resistant should be used here. So it's not like, oh, I come up with my own hash that it takes like, you know, I don't know, like I XOR all the bits together and I have a hash, because you can have a hash with whichever you want. You just combine the two bits and then create a hash, right? The idea is that your hash should be collision resistant, which means that it should be very hard to predict what is the outcome of this hash. Otherwise, the adversary can find two messages with the same hash and boom, your system is broken. All right, I think the last thing, or like one before the last thing I want to describe in cryptography is what we call authenticated encryption. The idea of authentication encryption, or AE, is that combining authentication or integrity and encryption together, right? So for example, there is, I want to send a message, but I want to, achieve two things. One is that I want to achieve confidentiality, which means that if somebody sees my message, they don't understand nothing about it. And you already remember that this was what we use encryption for. But I also want to make sure that this message that I'm sending is the message that is supposed to be sent. Right? I want the integrity of message. And if you remember, that was the part that we used max. So we have, CCA or, chosen ciphertext attack security and max security, and I want them both together. I want both max and encryption together. So the question becomes, which one of these two should I use? Should I encrypt and then compute the MAC, or should I first compute the MAC and then encrypt the whole thing together? Which one do you think is a good idea to do? So I have a message, I want to send it. I can compute the hash first, sorry, the MAC first. I have the tag, so I have my message, I have my tag. I can encrypt these two together, have one C, and then send this C, okay? This is option number one. Option number two is, I have my message, I encrypt my message first, I get the encrypted version. Then I compute the tag over this encrypted version, not the message. I get my tag and send this. Which one do you prefer? Which one do you think is a better idea? Suggestions? Yeah.
Maybe the first one, because the tag is also important to have encrypted.
So you choose the first one because the tag is not also encrypted. Anyone wants to take two? Yeah.
If you encrypt the message first versus both the ciphertext and the tag, wouldn't it be faster because the encryption requires a block cipher versus and it's a lot slower than the hash function?
That could be one, yeah. So the speed problem, but I mean the security problem here is more important. One of them is actually not secure, and the other one is secure. The one that is not secure is actually the first option. So you should not ever do MAC and then encrypt, because if you do MAC and then encrypt, it's basically becomes very similar to encrypting a bigger message, right? So you're not really having the MAC, capability here. And then remember that you don't care about confidentiality of the MAC, because we already kind of proved that nobody can understand anything about the tag. So what you would do is that what we call encrypt then MAC. So you get the message, you compute the encryption, you get the C, you compute the tag over the C and not the tag over the entire thing. Okay. And then there are known attacks that kind of shows that this indeed can be subject to kind of like substitution attacks and so on. So in order to have what we call an authenticated encryption, which is actually a gold standard in encryption, you encrypt your message separately. You get your ciphertext, you compute the tag of ciphertext, you send that together, and then you will get both of the good things. Okay. And then this is the last thing, and that is what we call digital signatures. So if you remember about MACs, I said that, okay, if I want to have integrity of MAC, I need to kind of find keys for both parties, because the one that computes the tag needs to use the tag, needs to use the key in order to compute the tag. And the receiver also needs to compute the tag similarly to the same way that the sender do that, and then compute these two and see whether they're the same or not, right? So this runs into the same issue that we had with symmetric encryption, which is how do I even send the key to the receiver? Okay, I can, for example, use like a CAM or this kind of hybrid encryption mechanisms, but there's also another way of doing this, and that's what we call digital signatures. So in order to kind of verify to many different users, there might be and there should be a way that we kind of use asymmetric encryption, similar way that we do asymmetric encryption in order to verify the tags. Okay. And that's what we call digital signatures. It's literally the way that we actually do the signatures. If you think about signatures, I sign, and if anybody sees my signature, and if they have some way of kind of matching my signature with me, they know that this is me. There is no additional kind of secret that needs to be shared between me and anybody who wants to verify, right? So anyone publicly can verify, only the secrets holder can sign. Okay, so this is the idea of digital signatures. How do we achieve digital signatures? We're going to use asymmetric encryption. Essentially, kind of like the high-level idea is that we're going to sign with our private key, and anybody who wants to verify, they verify with the public key. So different than encryption with RSA, for example, which we encrypt with public and decrypt with private. Here we sign with private and verify with public. Okay. The nice thing about this is that once I shared my public key with everybody, everybody can verify that this indeed is me. And this is actually the way that TLS works and all of our websites works. In order to understand that, oh, this is the website that we think it is, we always just use this digital signature. So very important concept in cryptography, actually. So how does this work? We usually use, again, hash-based digital signatures. It's another use case of hashes. Think about, the signatures as this, that I have my message. What I would do is that I feed this message into a hash function, again, a secure hash function. I'm going to get my digest. Then I'm going to use my inverse, trapdoor function f inverse using my secret key in order to get the signature. Okay. Then I'm going to share this signature with the ward. The ward, what they're going to do is that in order to verify this, all they need to do is that, again, they know the message because I send the message. They compute the same hash, and this is the signature that they're gonna. So they compute the same hash and they're gonna get the tag. Then they're gonna decrypt the signature. In other words, it's opposite of F, and then they're gonna get basically here. And they're going to compare these two together, and then if they match, it means that the message is coming from it. And again, the important thing about this is that knowing the signature, I cannot go back. I cannot sign myself without knowing the secret key, right? So similar properties that we had in RSA or any other asymmetric encryption mechanisms apply directly to here. Okay? Some final points. So what are blockchains? We're actually going to have another computer assignments on blockchains. The nice thing about blockchain is kind of combination of digital signatures and hash functions. So you will see this, that the use cases of a digital signature and hash functions is one of your projects. There's also, we're going to talk about side channel attacks on crypto system. And this is actually what we're going to talk about next week or week after. Where essentially all the things that we say that, for example, AES is secure, You cannot really find, the prime factors of RSA and so on. They're all true, unless the adversary has other ways of finding something about your system, okay? And these are what we call side channel attacks, which means that there are some value dependent activities that I can find in order to kind of extract the keys, okay? So just keep that in mind, that when we were talking about side channel attacks soon, you're going to see that we're not violating the theory of this, right? Still, all those things we said about, security of CCA and CPA and semantic security, they're all true. We just didn't have that one tiny bit of assumption, and that is, what if the adversary has more information about individual operations? And that's where the side channels come into the play. So this is kind of like, just keep that in mind, and then we're going to revisit this very soon. All right, so that's it with the crypto. Just we talked about encryption, decryption, symmetric, asymmetric. We talked about hash functions. We talked about MACs, and we talked about digital signatures. And again, as this is just scratching the surface of cryptography, there are courses, multiple courses on cryptography. If you're interested, definitely go and read more about this. But this is just what we need in this course and then there's also just generally what you might need as an engineer to know about cryptography. So that's why I kind of went through it. Any final questions about crypto? Cool. Let's have a break, and then we're going to start talking about sensor security, the new chapter.
Sorry.
Okay. So let's switch gears and let's start talking about sensor security, the new module. From now on, things become very system oriented, so no longer theory or math, unfortunately. I don't know if you like it or not. Quick reminder about the paper reviews and presentation. I mean, there's no review, it's just presentation. If you want, you can definitely read the papers. So the schedule, I think, is on the website. If there is any problem, let me know. There might be a few kind of duplicates and so on and so forth, which we kind of like just realized there's one at least for now. So we have to kind of make adjustments. As a result, some of the groups might not be exactly 3, some of them might end up being 2 or even 1. But we cannot really change and move things anymore. I tried to kind of like keep everyone in the groups that they wanted and present the papers that they wanted, but I think there were like 1 or 2 instances that I really had to kind of move either the groups around or the people around, or the papers around. So apologies. If you're taking if you're enrolling in the course like very recently after the deadline, just again do the sign up, and then I'll kind of either add you to an existing group that doesn't have enough people, or assign a new paper. If you're a master's of online student, and then again you kind of enroll, submit the form again, and I'll assign. I think I updated the list today with some new students. Go and check it out. But yeah, anybody has any questions regarding paper presentation? You good? Yeah. Can you get email of what? Oh, the email ID of the other people in the class. I cannot share emails ID of the classmates, but you can probably just find them on campus fire. They're there. So you can message them directly. If you cannot locate them, let me know and I can email them. But everybody should be on campus fire. There is like a small chance that, for example, people drop the course, and that might be one reason that they're not there. If you can locate them, message me, and then I'll email. I'll check the list of the who is unenrolled and who dropped the course, or I'll just message them directly. Any other questions? All right, so let's move back to the computing system. And if you remember, like kind of like the last time, and the reason that kind of we jump into cryptography was we wanted to boot our system into a good known state. And for that, I told you that we need to kind of like check the integrity of the system, and we need cryptography for that. Now we have enough knowledge of cryptography. Let's actually continue the story that we wanted to tell. And that is like, we want to make sure that the system at least is started from this kind of base trust that we have into something that we kind of like can run programs on, and then hand the control to that part, and the rest is kind of, as I said, is out of our control because there's like a lot of things to check that we cannot do. And that would be the story of the rest of this class. But at least let's actually get to the point that we can do something meaningful with the system. And that's part of the secure boot. And if you remember, I said that the trust starts with this trusted platform module TPM. And then we're going to bootstrap our trust on top of this TPM. Now we know a little bit about cryptography. Within TPM, we actually have pair of keys. Usually this is like at least one symmetric key, and then maybe a public key and secret key, and then some cryptography functions such as like secure hash functions and max, and some encryption decryption if needed. And then essentially we call this TPM the root of trust, the base of our trust. Everything else is built on top of this TPM. So how do we actually build the trust on top of TPM? We're going to use this protocol called attestation protocol. Okay, we're gonna talk a lot about attestation later, but the basics of attestation for this particular concepts of secure boot is that we're gonna trust the base, and at the beginning that base is just the hardware. We're gonna ask the base to compute the attestation report or check the very integrity and correctness of another layer. If the base kind of verifies that, now we can trust that and we can hand the control to that. So you kind of think about this as kind of like a building a house. That we start with the foundation, we trust this foundation. We don't necessarily start with the like very large foundation, because if it's the foundation is large, then it's very hard to verify. So we start with something very small, but we have this capability that if we want to add another layer on top of it, we can ask this part that we already trust to compute the integrity of this. If it matches with what we expect, now the trust is kind of bootstrapped. The trust is extended to the next layer. And then we keep doing this over and over again until we reach to a point that say that, okay, from now on, this is kind of like we have enough. And this is the control to you operating system. And then you will start doing things. And then we're going to actually talk about what from that point on we cannot really kind of continue this method. In fact, we can, but it's not scalable anymore. Okay, so we do this process of repeating. How do we actually do that? This is actually part of one of the protocols that we do is this unified extensible firmware interface, or UFE, that essentially starts at the top here. So this is like the security layer. The security layer measures, and when we say measure, you can think about it as kind of computing a hash function of the code of the next section, and then comparing this hash with the hash that is already stored inside this security function. Okay. Nope. Sorry. It's frozen. All right. Okay, there you go. So we hash is kind of computed, and the hash of this part is stored here. What we're going to do is that we trust this. We ask this to compute the hash of this. It gives me a hash. I'm going to compare the hash with this value that is stored. If the two hashes matches, then I trust this. And then I repeat this process over and over again until I add all of these things. For example, I need to check that my memory has been initialized correctly. I check my drivers. I check my boot sequence and boot drive selections. Like there are a whole bunch of details that I'm not really wanting to go through them, but just keep in mind that there are steps. Okay. And then kind of like this is more of like to give you an idea that we use this secure hash function that we start with like the TPM, then the bootloader, we compute the hash of this, we put the hash in this next one, we compute the hash of the kernel, we put the hash in next one. Eventually, we're going to have a big hash, a chain together of all these things. And this hash, if this is the correct one, that means that all these individual components can be trusted. My OS kernel can be trusted, the kernel module can be trusted, the bootloader can be trusted, and so on and so forth. By trusted, I mean that the kernel hasn't been modified, right? It's the same thing that I installed on the system, right? That's the least that we can do. That whatever you design, this secure boot sequence can guarantee that this has been loaded properly, okay? Whether or not, for example, that thing that you've designed is secure or not, or bug-free or not, or is resistance against future attacks or not, that's a separate story, and we're going to actually get to that. But what this does is just generally saying that we loaded the thing that we think we loaded, and that's the same thing that you as a developer or programmer or manufacturer loaded into this thing. Okay, that's really what the secure boot does. Okay, and then again, there are details for it that I specifically skip, but eventually we're going to get to this point that we have the kernel module, which is in the base of an operating system, and then after a while we don't really care. Okay. So what could go wrong after this? Like, why are our systems is no longer secure? Like, what would happens after we kind of pass the control? Okay. The reason that our system is no longer like, it might get insecure, it might get attacked, is our system's going to start interacting with the real world. Okay. And unfortunately, there are a whole bunch of bugs at the hardware and software that the adversary will exploit in order to kind of change things in my kernel, in my software, in my hardware. And that's where the attacks start. Okay. If I had my system in isolation and I did the secure boot and really don't talk to anybody else and doesn't get really impacted by anything else, my system would have stayed secure. Okay, so it's not like security is this magical things that never will be achievable. It can be achieved if we just kind of disconnect everything from the computer. The reality, though, is that your system your computer is only usable if you can interact with it, right? So, and then unfortunately, if you can interact with your computer, the adversaries can also interact with the same computer. As a result, things can go wrong. Okay. If you remember, I'll show you this slide and say that, okay, all part of the system is vulnerable. In this lecture, I want to kind of focus on this sensing and actuation part. That's kind of like the first step, the kind of the gateway toward the world of computers. Sensors is kind of like really what it does is changing the physical domain into some analog domain and then some digital board. So it's really kind of like, as I said, it's kind of a door to the system, right? And then it interferes with the environments and they're also kind of like they're vulnerable to the faults as I'm gonna describe soon. And sensor itself is very, very rich and very, very interesting area of exploration and research. It has been many, works in this domain, not necessarily for security, but generally sensors, since they have different modalities, they have different paradigms that actually can kind of enable new things. Think about, for example, your smartwatch. All these sensors that are packed inside this watch now can do lots of different things. Like, you have gyroscope, accelerometers, I don't know, like even like EEG, ECGs, like pulse, all these different things that it does, and it translated into some like higher level perceptions. Very interesting kind of area. But unfortunately, again, since you can access the sensors, the adversary can also access the sensors. That's the problem with sensors. And then similarly, the kind of like actuation domain, that is the kind of like the connection between your system and some physical events, can also be impacted by this, right? And actuation is actually usually much more significant because that's really have like some physical impact. So for example, think about an autonomous driving car. If an adversary managed to kind of hack into the system and change the outcome of the system, what could happen is, for example, they can cause a crash, or they can like cause another system to fail as well. So it's kind of like you will see the physical impacts of this to the environment as well. In both cases, generally, this kind of like sensor actuators where kind of like our story begins. We're gonna mainly, as I said, the focus of this course is IoT systems, because that's where you see all of these different sensors and actuators. So we're gonna talk about this kind of like the rest of this lecture and tomorrow. Next lecture. All right, so let's focus on sensors. As I said, sensors are extremely diverse. There is more than 300 different types of sensors these days. And there are a whole bunch of different ways of convergence, right? So you convert a sound to, I don't know, electrical signal, you change a vision or physical, change of colors into, again, some numbers. So there's many different ways of using a sensor. As a result, unfortunately, there are many ways of attacking the sensors. As you can see, you see this duality of the more accessible things becomes, unfortunately, the more accessible it is for the attackers as well. So that's kind of the duality. So if I want to kind of like give you a more systematic way of thinking about sensors, because one thing that you will see is that for all these attacks and defenses, eventually, at the end of the day, what you need to do is understanding the underlying physics and operation of anything. So for sensors particularly, there are kind of three main components that you have to pay attention to, okay? There is this physical domain that's kind of like, as the name suggests, is part of your physical. This is kind of like a measurements that are happening. And then there is some form of, signal that generates some form of activation that is generated, and this activation is transduced into some form of analog signal, right? So the big thing about sensors is this transduction, which happens from a physical phenomena to an analog electrical signal, right? Then this analog part usually goes through an analog circuit. There's usually filtering and amplifying and so on and so forth. And then eventually the analog domain is converted to the digital domain, right? It becomes like zeros and ones. And that's where you're going to have your digital word. And then, of course, if you have an actuation, you're going to do the reverse process of this, right? So any sensor, if you want to think about it, has a collection of three things, right? The physical word, the analog word, and the digital word, okay? So in the context of attacks, where do you think the attack might happen in this digital, analog, and physical world?
All of the above.
All of the above. Can you maybe start like giving examples where you think things can happen? Anybody else? You could, yeah. For one of these three, can you give me an example?
Spray upside down, compress air to make the chip cold, and then change its operating conditions.
So changing the operating condition of the device in order to create a different scenario. So you kind of change the physical world in order to create some errors to the system. So that's a physical. Anyone wants to kind of get into the analog? Yeah.
You can inject some noise into the analog signal.
Yeah, so you can create some faults, inject some noise, shoot some lasers. There are actually ways that you can do this so that you're not changing the physical world, but you're changing the operation inside the analog. Does anybody know any examples of a digital one? We can actually talk about this. It's yeah, you know some?
Origin works, but I mean, like you said, we wouldn't.
Yeah, for example, changing the hardware. There's a whole bunch of what we call macro architectural attacks that can also happen in the digital world as well. We're gonna actually talk about them. The papers that we're gonna review next week, people are gonna present, gonna have examples of all three actually. All right. So yeah, what we can change, as I said, we can change anything. In more specific, we usually have 4 different kind of attacks that we can consider in sensor systems. The big one is what we call transduction attacks. Essentially, the idea of transduction is we change some physical property, and that physical property translates into some digital values that are going to cause issues. The nice thing about, I mean, nice in terms of attacker is changing physical properties are very easy because this is the physical world, right? And the defender has no control against it. So you cannot control the temperature of the environment. So you cannot control the temperature of this room from the device itself. There needs to be another additional thing that's kind of do that, right? So if I can kind of change the physical world around the device and that translates into an attack, that's a very, very powerful attack, right? So that's what we call transaction attacks. We're going to actually give you a few examples of this. Another thing that we can do is that we can do what we call denial of service attacks, okay? That we're not necessarily interested in kind of changing values, but we are just interested in kind of like breaking down the system. That's like stop the system from work, right? So for example, like melt down the entire system by raising the temperature or doing various different things, right? Another kind of things that we want to do is integrity faults, integrity and fault attacks. That we're not necessarily interested in like sending incorrect values, but we want to kind of flip things as the things are moving forward, right? So not necessarily changing the physical environment, but as the data is moving toward various different, either at the analog stage or digital stage, we create this fault such that the numbers are flipping. We want to talk about that. And then eventually, of course, at the digital level, we can do various different attacks. I'm not going to talk mostly about digital for now. Later on, we're going to talk about it. So what are the attack impacts? The attack impacts is the same availability, integrity, and confidentiality that I talked about. There's nothing new here. It's the same thing. The attacker's goals is still the same. They want to attack various different things here. So what are the different types of transduction attacks, do you think? Can you give me different modalities for transduction? Remember, transduction is that I change the environment in order to cause some issues to the system. Okay, yeah.
If you have like a hot monitor, you could maybe move it to the different location.
So move it to another, so we kind of fool it to read a wrong value,
Yeah.
right? Okay. Anything else? Yeah.
Audio, adding this audio.
Adding noise to the audio is an example, yes. Anything else? Yeah.
If you have some sort of like image sensor, maybe you should have like a laser shine into the sensor that's called.
Yeah, so if you have some form of a camera image sensor, you can add pixels, remove pixels in order to, cause the issue. Yeah.
EMI. Oh, EMI.
EMI, so you can create electromagnetic injections to the system, and that will cause an issue. Anything else? You can be, like search your internal evil to come up with idea. Any other suggestions? Have you heard about any cool, physical attacks ever? Any more suggestions? Yeah.
There's like voltage glitching where you can take a MOSFET and power on and off the power supply.
Yeah, so you change the power supply and changing the power supply will also create glitches. Yeah, these are all great examples. There are various different types, as you said. There are electromagnetics, or generally the RF domain. There is the sound and acoustic domain. There's the magnetic field that you can change. There's the electric field that you can change. There's the light vision or light domain. And of course, you can create movement of force. So you kind of like, actually hit all the possibilities here. Important thing about transduction attacks is this notion of what we call in-band versus out-of-band. Okay, in-band versus out-of-band is this, that any sensor has an operating range and operating modality. So for example, you have a camera, it only sees visible light. It doesn't see infrared, it doesn't see ultra, violet, it doesn't see any other range of light, okay? So when we say inbound means that, for example, if you have a camera, if the attack happens during that operation range, that's the in-band attack, okay? But the interesting is that lots of these attacks actually happen out of band, which means that the adversary changed something outside the operation range of the system, but that somehow translates into the operation range of the attack. And these are really hard attacks to detect because the sensor has no understanding of this is really happening. They cannot, in other words, see it or measure it. Another thing is that modalities. Sometimes, for example, you have like, I don't know, a microphone, but then you kind of launch, you change the temperature, or I don't know, you launch a laser, you do something else in another modality, and that will introduce attacks to this modality. And that's also kind of considered out of band in terms of modality in the system. So keep that in mind, okay? Yeah.
If you attack the out of band, including the device, because that will not be right, that's again.
Good question. Like the question is, how does an out of band attacks is actually really happening? I'm going to actually give you example. I think we have time. We're going to get to it. You're going to see an out of band attack. There's like a very cool one called dolphin attacks, which what happens is they actually create some sounds that was way above the range of hearing range. But what they showed is that I'm going to actually have slides for it, but let me explain it. So what they found is that the microphone itself, the frequency response of a microphone is not a linear response. So what will happen is that if you have like something like, let's say the signal you have has an F1 and F2, F0 and F1, that it has, let's say, two components. This F01 is within the band, but this F1 is outside the band, okay? If your receiver is a nonlinear receiver, you're going to have like terms like, A S plus B S2 or something like that. So it's a nonlinear frequency response. And then if you actually kind of like modulate this, if you know anything about like communication systems, usually kind of like, multiply this to another term. And then as a result, you will get something like, F0, F minus 1 or something like that. So you get a subtractive term. And that subtraction is what's going to then end up in your band. And as a result, you're going to actually creating something in higher band, end up in your lower band. Similar way that we send communication signals, right? You send it into a higher frequency, end up in a lower frequency using some filtering. So actually, like, yeah, there's interesting things in dolphin attacks. All right. So now it's actually good questions is that, again, if you remember, I told you that you always have to consider what is the threat model, what are the attacker's capabilities, what can be changed by the attacker. And as I said, for transduction, these are many things the attacker can do because essentially you cannot control the environment. But let's, for example, say that we know that our computers are in this room, and nobody can kind of like come inside this room, or nobody can change the temperature of this room because, for example, let's say the thermostat is also controlled by me, okay? In that words, for example, we can say that, oh, okay, changing the temperature and kind of frying this device is not an option. But maybe somebody can, for example, install an antenna outside and kind of send like very strong RF signals to the system. Maybe somebody can install a giant speaker, and this giant speaker can kind of, for example, send acoustic signals. So you have to really care about what are the attacker's capabilities in any of these transaction attacks, okay? So this includes like equipment, the range, the time, the access, the power of the attack, and so on and so forth. And another important thing that you have to remember is that the attacker trying to attack the physical domain, the analog domain, the digital domain, or all of the above. And finally, you have to also understand what is the goal of the adversary. Is it a denial of service attacks? Is it an integrity attack? Or is it more of a confidentiality attack? Okay, so these are the things that we need to consider. There's also this very nice paper that I recommend you to kind of take a look. What they did was kind of try to kind of systemize and create like a formal model of transaction attacks. Essentially, you can kind of like show the transaction attack as kind of series of different functions. And these functions are kind of like, there is like a transfer function for these. So for example, you have your transducer, you have your signal processing, A to Ds. Each one is basically a function, right? And then if you are an attacker, you can introduce noise at every different in every different part of the system. So this generator function, which is the attacker function, can create kind of like, a transfer function at any of these. Of course, changing anything during this process might be very difficult. So not necessarily all of these things can be happening. For example, maybe this one is not possible for the attacker. But if you want to model this, essentially the model could be, you can assume that everything is an input plus some noise and some transfer function, right? If you can model every single component of our system like this, then we can know for sure that how much system is robust and how much system is vulnerable against different attacks. Okay, that's kind of the whole point of this. It's kind of like, this is like where the entire kind of derivation is coming into play. Okay. And then the important thing is that, systems should be designed such that they're actually robust against these noise. So you can actually then, when I have this kind of transfer function here, then I can predict that, for example, oh, this amount of noise is the amount of noise I can tolerate before the outcome or the output of any of these functions are actually different, right? So this is the way, as a designer, you want to know this. You want to know your transfer function of your entire system and individual components, such that say that, okay, for example, my system can tolerate plus 10 degrees of temperature change without really anything will happen to the system, right? Or, as I said, if you actually kind of like divide this into smaller components, then you can say that not only here, but maybe if the adversary introduced another noise here, my system is still robust. So it's more of like the design aspect of the system when you're doing this. Non-related to sensor security is that we're gonna post the first computer assignment tonight, hopefully. So please just start ASAP. I think that we're probably gonna set the due dates next week, sometime mid next week. So you should start as soon as possible. It's going to be about cryptography. We're gonna give you a Jupyter notebook. You have to go through like different steps, like basics of just do a simple encryption, then attacking it encryption, do some hashing, stuff like that. Okay. And if you have questions about the computer assignments, one thing you could do is asking on CampusWire. Okay, so use CampusWire to ask questions about lectures, about the projects, make it interactive. All right, so let me give you some examples to kind of like give you some vision of how these attacks works. Next week, actually, in the presentation, you will see some more. So on the sensor side, it's all about really implementation. The first one is actually an interesting paper. It's called Rocking Drones with Intentional Sound Noise on Gyroscope Sensors. The idea of this paper is, we have drones. They have these giant speakers that kind of sends sounds to the drone, and they found that there's specific circumstances that will cause the drone to malfunction and eventually crash. Okay, so how does it work? Drones usually typically use this MEMS sensors, microelectronic mechanical gyroscopes, in order to kind of balance, right? So to know where they are. They usually have multiple of these gyroscopes to kind of find the altitude and the direction and so on and so forth. They are basically the gyroscopes. If any of you are familiar with gyroscopes, is basically based on sensing vibration and translating this vibration into some values, right? And based on these values, then someone can understand, for example, where we are, whether we should kind of like tilt left or tilt right and move forward or move backward, etc., etc. Most of these gyroscopes has what we call a resonant frequency, right? So probably you're familiar with resonant frequency, where the vibrations, if they happens with a particular frequency, that results in a very significant number. Okay. And what this guys did was that they found that there is this achievable resonance frequency that if they intelligently kind of create that resonance, they can actually fool all the gyroscope at the same time, and all gyroscopes kind of experience this malfunction altogether. As a result, the system thinks that it's a different altitude or different speed, and then tries to kind of like fix himself, but it cannot, and then eventually will crash. Okay, that's really what the attack does. This is their kind of system. What they did was kind of the red part is their attacks. and the kind of blue part, the white part is the system. So there is actually a drone that kind of like, the drone obviously is controlled by some form of a flight controller. For example, in this case, I think these guys did it with an FPGA. And then of course the flight controller is connected to some sensor, some gyroscope. Okay. So what these guys did is that they say that, okay, I'm gonna have, let's say, a microcontroller like an Arduino. The microcontroller gonna create some sound signals. Okay. And then they have this sound card that's kind of like, create this sound, the specific patterns of sound. And then of course they have amplifier and speaker to kind of broadcast this sound. But this sound creates, specific signal, audio signal that creates forces gyroscope to resonance. Okay, so it's like a specific frequency. These sounds are created. They're powerful enough and a specific frequency that causes the resonance in the gyroscope. The results of that is that the system crashes. Okay. This is actually the results of the crash. These are, I think these are the top left ones are the results of the gyroscope. And there is actually, I think there are 4 different gyroscopes in the system. This one's are the top 3, like, left, right, bottom, and down. And then as you can, and this is like the x-axis is time. The y-axis is kind of the value of has been read by the gyroscope. And as you can see that the attack is kind of working like this, that, initially nothing happens. At some point, the speaker is just kind of broadcasting the sound. As you can see, the moment that this happens, you see like very, very random patterns of the gyroscope. I think this one is, this one, the speed of the rotor of the drone. As you can see that it used to kind of like, gradually going up and kind of like, fixing at specific speed, but then you will see all these kind of random ups and downs and behavior as the attacker is actually sending this kind of like signal. And then the interesting thing is this is the altitude of the drone. It was kind of going up at this moment where the attack started. So you see there's sharp kind of drones going down and then actually hitting the ground. And yeah, this is the transmitter. This is like where they actually send this signals. The kind of like the takeaway from this is, let me see if I have another slide for this. The takeaway from this drone attack is if the attacker knows the physical functionality of the device, they can kind of manipulate this in order to do some malfunction. In this particular case, this was a gyroscope that was vulnerable to resonance. So the attacker can create that resonant frequency and cause the system to fail. And unfortunately, it was like feasible enough by using a small speaker and a device like an Arduino. So that's like a huge thing to consider when we are talking about, for example, drone. Right? Any questions? Next one is an attack to a medical device. Let's actually pause here. We're going to talk about this next time.